Okay, so welcome to week 7 of Electrical Machines 1 course. So today we will be starting a new chapter, that is DC machines. So till last week we have discussed several concepts on transformers, and from this week we will be discussing new concepts on DC machines. So before getting into the session, I'll just give a brief overview of what we will be discussing today. Today our entire focus will be on the winding terminology which we are going to use in a DC machine. So in a DC machine, we have stator, rotor, armature winding, field winding, and slots, rotors, and all coils, turns. So uh, before getting into the actual EMF generation and other concepts in DC machines, it's very important to know the all kinds of basic terminology in inside the DC machine. So how coils is being wound on a DC machine, how the coils is being wound on armature winding. Such concepts we will be seeing, and I assure that these concepts will be very much interesting to you all. And yeah, we will see such interesting concepts in this week session. So yeah, let me start. So yeah, here you are seeing a DC machine cross-sectional view, and if you see, uh, so here let me take the pointer. So yeah, these are stator poles, NS and NS, north, south, and south, and the markings you see on each pole are the windings, and we call them as field windings. The windings on the stator poles, and the center uh, structure you are seeing, it's a rotor cross section, and on the rotor you can see the slots and as well as teeth as well. So this particular like this is called the slot, and this is nothing but the teeth. So when you have made enough teeth on a rotor, you will get the slot structure. So from seeing this diagram, can you tell me how many poles this machine is having? Is it a two pole machine or four pole machine? Yeah, please feel free to answer. So yeah, it's so from seeing the diagram, we can say that it's a four pole machine because we have four poles: north, south. We have four poles, and you can see on the rotor side we have different slots. If we count those slots, we will get number 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it's a 12 slot rotor, four pole machine. So under each slot, can you tell me how many slots we'll have? Because we have total 12 slots and we have total 4 poles. So slots per pole will be S by P. That is, number of slots is 16. Yeah, yeah. Number of slots is equal to 16. Number of poles is equals to P. That is S. I'm just denoting by alphabet so that we'll be using those two alphabets down the discussion. Slots per pole will be, sorry, it's 4. 16 by 4 is equals to 4. So we can say that under each pole, this is the pole, we can see 4 slots: 1, 2, 3, 4. So these 4 slots come under the this south pole. Now coming to this north pole, we can say 1, okay, 1, 2, 3, 4. 1, 2, 3, 4. Okay, okay, sorry. 4 pole. Acha, this is not 16 slot, it's a 12 slot. I'm sorry. That's the problem. Okay. Why can't I do that? Okay. Yeah. Slots are only 12. Poles are 4. And 12 by 4, it will be 3. See, for each pole we can say 1, 2, 3. Let's say these 3 poles are currently under south pole, and next 3 poles are under next north pole, and next three slots. Next three slots will be under the south pole, and next three slots will be under this north pole. So each pole is having a span which covers three different slots. So that's what we call slots per pole, or it is also called as coil span. Because if we wound a coil, if we start from one slot, let's say we start a coil from this slot, and this will go there, and it should return from this slot, because this is how a coil sorry, it should return with it should cover three slots, because each slot starting and ending should be coil span, and that span should span out under each pole. So that's what. Just erase this mark because we. Okay. Yeah. So now now each slot will have two coil sides, because when we talk about a double layer winding means, let's say this is a slot. Now I'm placing two coil sides. Let me just draw a coil first. Let's say this is, I took a coil and I have wound it in this fashion. It's a two-turn coil. I can take a two turns. So yeah, let's say this is a coil. This entire wire is a coil. Now this is coil side 1, and this is coil side 2. So what I meant was, each coil will have two coil sides. Now if you see this coil side cross sectionally, this is that one, this circle I have shown. So I'm placing like this. This is a coil, and I will wound it, and it will, let's say this is another slot, and this is coming like this. That is the return path of the coil. Now this coil, and this is coming back like this, and these are the terminals of the coils. So that's how you have to imagine when I draw this kind of coil sides inside the slot. Now with that idea, we will see. Let's take a double layer winding. Double layer winding means, see, if in each slot we are each slot is housing two coil sides. So this might be, let's say we have two coils. This might be one coil, and this might be another coil. So each slot is housing two coil sides. Now if you see, we have how many slots here? We have 12 number of slots. Now since it's a double layer winding, and it's a double layer, it is having two coil sides. Now I'm placing each slot, I'm placing two coil sides. Yeah, if let's say this is one coil, and this end should be after coil span is a 3, right? 1 2 3, this particular coil. So this is the starting, and I'm making a coil place here, and it will return here, because the return path we usually place at the bottom side, and the top side we will start the coil. So that's why I marked this as the bottom side. So if you see, this 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 coil side and this coil side constitutes one single coil. Now if you count like that, you will get how many coil sides, because it's a double layer winding. Now if you see, this two constitutes one coil, and now this is the return path of some other coil where it might have some other place. If you see 1 2 3, so this particular coil, it is one coil, it is having two coil sides. Now if you see like that, the total number of coils you will get is 12, because that's equal to the number of slots. So because it's since it's a double layer winding, number of coils is equals to number of slots. Simple, because we are having number of slots is what, 12. Each slot is having two coil sides, right? 12 slots, each having 2 coil sides. That means we have 24 coil sides, but each coil will have 2 coil sides. So if you are having 24 coil sides, how many coils we have? 12 coils, which is nothing but number of slots. So for a double layer winding, we can say that number of coils is always equals to number of slots. Yeah. Now let's see. Uh, let's say we unwound that rotor part. So here we have a rotor like this, right? It's like a circular structure. What I will do is I will take a cross section like this and I will make it parallel. I will just make the diagram here, then you will get an idea. Like this. I'm just drawing it in planar structure, like in a straight line. It's just I have, this is the slot we have, right? I have just made it and made it like a on a plane. So that is this one. Yeah. So yeah, like this. Let me take how many coils should I take? Okay. Let's take S is equals to 16. 16 slot machine I'm taking. Poles is equals to 4. 4 pole machine. Now if you see, let me see, color. Okay. I'm just marking 1, 2, 3, 4, 5, 6, 7, 8. So like that we have 16 slots, right? 15, 16 and 1. Because after 16 slot we will come back to the 1 because it's a circular thing. Now yeah, now I will place my first coil, you know. So this is my coil 1, 2 turn coil, sorry, yeah, let's say this is my coil 1 and yeah, I'm starting with my slot 1 because I'm starting my coil placement, winding placement from slot 1. Now I told you already, in a double layer winding, my starting part of the coil I will place on the top and the return part I will place on the bottom. So I am placing, let me take another color for, okay, coil 1 is already red color, I am taking red here. I placed one coil, okay. So where it should return, the return part of the coil should be in which slot? For that calculation, what we will do, just now we calculated, that is a coil span, right? S is equals to 16 and P is equals to pole. 16 slot 4 pole machine. Now S by P is equals to 4. Now this is nothing but my coil span. Now my coil span is equals to 4 means we can say that coil span is nothing but how many slots that coil should span. Now I have started with 1. Now add 4 to that. 1 plus 4 is 5. On this 5th slot, on the bottom side, my coil 1 will return. So yeah, this is how I place my first coil. Now yeah, out of 16 coils, I have completed placing my coil 1 because it's a double layer winding. I will have 16 coils for 16 slots. Now let's place my second coil. Again, I will start with second slot. I will place another color. Let me take. Okay. This is my coil 2. And 2 plus 4, it's 6 on the bottom of 6th slot because that's a return path. I will get the second coil number 2. Now in the same way we will keep on placing all the coils. Now slot 4 will have slot 8 return path. Now slot 3 will have its return coil path at 7. So that's how we place. Now let's make a winding table. It's very simple, and at the same time, it's very interesting to see how these winding tables and how these winding connections are being made in a DC machine. It's very interesting, and how the voltage is generated is very interesting. I request you to pay attention while we draw this, because it's pretty fascinating to see how a winding has been is being made on a DC machine. The concept is very interesting. So let's say now I'm trying to draw this coil. Let's say this is simplified. So this is the notation I'm taking to draw a coil. Now see, I'm just this is my coil one. So coil one, I'm starting with where? I'm starting with one. So this is the one slot one, right? I started with slot one, and the return path is for 5. So for the return path, I will mark it as 5 dash. Okay. Now coming to slot number 2, I started with 2.
Sir,
Yeah,
hello. Sir, I have a little question on that. In 12 slot or 16 slot, there will be equal slots in each pole, na? And in slot 12, there will be three pole in all pole, three slots in all pole equal.
okay. If it is like, let's say you have how many slots you said?
Sir, in 12 slots or
Yeah,
16 slots,
yeah. If even it's
they,
short slots or
there 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 will be equal slots like 4 3. Na?
yeah, yeah, yeah.
Okay, okay.
Not three slots. You can't say the number. You have to divide slots per pole S by P. If it is three, if it is four, how many slots per pole you will get? That number will be equal throughout the structure.
Oh, we have to divide the slots by pole.
Yeah, slots per pole. If you see this
Oh,
S by P, you can know that
okay,
how many slots are under each pole.
okay, sir. Thank you.
Okay. Yeah. Now I will quickly draw the rest of the 16 coils. So 6 dash. These are 8 coils. 1, 2, 3, 4, 5, 6, 7, 8. So yeah, I draw the 16 coils and I will just quickly make the numbering. 3, 4. If 3, it will end at 7 dash. Like it's because it's the coil span is 4. 8 dash. 5 will end at 9th slot. 6th coil will end at 10th slot. 7th coil will end at 11th slot. 8th coil will end at 12th slot. So 9th coil will end at 13th slot. 10th coil 14th slot. 11th coil 15th slot. Okay. Now here there is an interesting see. They have only 16 slots, but we are getting a number which is more than 16. So at that situation we just have to minus it from 16, because the 13th coil, let's say here is a in between there is a 13th coil. Like place 13th coil here. It should come in the fourth span, right? 14, 15, 16, 1. So the return path will be in the first slot. So when I say it's 17 dash, it's not 17th slot, but it's a first one. It's coming back. So it's whenever it's coming, we just have to write it as 1 dash. But it's like a return path. It's a closed structure. Now when it is 18, it's nothing but 18 minus 16. That is 2 dash. 15 will come at 3 slot and 16 will come at 4 slot. See next one, it will be 5 dash. So it's like a complete circle has been made with 16 different coils. Now my placement of all coils has been done. Okay. Now what is my main aim? Whenever I wound my winding into a DC machine, my aim is to rotate the machine. In order to rotate the machine, we will give an AC supply, and the output will be, of course, it's a DC machine, we need to get a DC supply. Now, how the DC voltage will be coming, we will see that a bit later. But right now, when we give an alternating supply to our winding, and it is all these coils I already told you. See, I just again marking here. Now, slots per pole is 4, right? So that means that my first 4 slots will be under the influence of either north pole or south pole, where at any instant of time the motor will be rotating. The motor will be on top of the pole. The no- at any instant of time, if you see, you take a screenshot of the photo of a motor, and if you see that at every instant of time, each pole will have 4 slots under it. So let's say it's a north pole. The first 4 slot will be under north, then 5 to 8 will be under south, and 9 to 12 will be under north, and 13 to 16 will be under south. So this is how each pole will have its slots. Now in the same way, like let's say, see, if you see, you're seeing 16 coils here. Now what I will do, I will connect all these coils in series, because that's how I'm going to get a voltage, right? I will connect these two, these two. Yeah, I'm just simple. I'm just doing a simple series connection. Yeah. Now 12 will go to 9. Again 13, 15. Okay, this 4 will come back to return path. Yeah. That's why I'll get a series connection. See, now I have connected all in series. Now all coils are rotating under magnetic field. See, because whenever a rotating conductor under the magnetic field, what will happen? EMF will be induced. That's a Faraday's law. Now, the polarity of EMF we will have to observe. That point we have to take care, because each each coil is under uh, one of the pole inside the motor. So first 4 coils, let's say, are under the influence of the north pole of the motor. Now, see, another question will arise. Now when I connected all in the series, it's like it formed a loop of 16 coils. Now there will be no circulating currents flowing in this loop, because if you see the polarity of the voltages, what the polarities the each coil is having, when we do all the sum of all the voltages, it will be 0. That we will see now, because see, let's say this is a north pole. uh, there are four slots under north pole, and other slots are under south pole, right? Now under the north pole, let's say these are having positive polarity. The next 4 slot which are under the south pole will have reverse polarity. So that's what we should take, because EMF induced is proportional to dLV sin theta. Now the D is your field, and the length is length of the slot, and V is the velocity. And using that convention, under north and south pole, the field direction will be opposite. Now let's take it as a positive. Let's say in my coil 1, the voltage induced is of this polarity, plus minus. Now the first 4 coils will be under north pole, right? So this is from here you can see first 4 coils will be under north pole. Now the next 4 coils will have same polarity, plus minus. Now coming to 5 to 8, these coils will be under south pole. So the polarity EMF induced will be reverse, minus plus. Next 4 coils again will come under north pole. One, two, three, four. Okay. From 13, we will have minus plus. Last 4 coils will be coming under south pole. So this is how the polarities will be, and this is how the windings polarities will be when they are connected in a series condition. Now see, the first 4 slots will be under the north pole. That's the polarity we assume. So next 4 slots will be definitely will be at the south pole. Now, yeah, that's how the rotation will be. See, from the starting, if you see plus minus, the voltage will get added here because the same polarity connected in series, voltage will get added. Next, we have four negatives. The voltage will get subtracted, and again four will be added, and next four will be subtracted. If you see that the total sum comes to the zero, so we can say definitely that there won't be any circulating currents within the loop. Now see, this is the coil one, right? I'm just drawing it again here. Two-turn coil I'm taking. It could be any turns as well. That's not a issue. These are the output terminals of coil one. Let's say this is the starting terminal, and this is the finishing terminal of coil one. Now I'm placing my second coil in series. Sorry. This is this is the starting terminal of coil 2, and this is finishing terminal of coil 2. Now what I'm doing, I'm connecting these two in series connection, right? So this is how my series connection will look like, and again it will here from here all the 16 coils will come. So this type of connection we call it as a lap winding. Why it is lap winding? Because I just showed you like separately side by side, but in turn how it will be like now. Let me take another coil, another color. The second coil, it will come as close as this, like this here. Sorry. Yeah. If this is coil 1 S1 F1, this is coil S2 F2, because we are starting the second coil right adjacent slot to the first coil. So it's like the second coil is on the lap of S1. It's like overlapping. So that's why we say this kind of connection as a lap winding. Lap winding. So yeah. So now the question comes is, see, till now we haven't discussed how we are getting DC output, because till now all the voltages are AC induced, alternating nature only, because we given AC supply, the voltage induced will be also AC in nature. But what we require, that is a DC, is a DC machine, right? So that part we haven't discussed. Now we will see how we are going to get DC. Yeah, yeah, yeah. So let's look at the next slide where we have placed. Now I just marked all the 16 coils with its starting S1 and finishing terminal F1. Now the same way we can see 16 different coils connected here. Now we can see all the 16 coils are displaced, and all must be connected in series. Now let me just quickly connect all the coils in series. Now this is the first coil S1 at the bottom, you see S1 F1. Now F1 will be connected to S2, right, and F2 will be connected to S3, F3 S4. I will just draw quickly. F5 S6, F6 S7. Actually, this the principle of this EMF generation and DC output voltage like generation is very interesting. If you just see how the DC has been getting, the technique is really interesting. Okay, now see, we have connected all the coils, 16 coils in series. At this instant of time, if you see, this is, let's assume this is a snapshot at one instant while the machine is rotating. I just took a snapshot, and I see how the coils are arranged. Now at this instant, we can see the first four coils. Now coming to sorry, S1 to S4 will be under the influence of north pole. That's what we are assuming, right? Assuming means that's how it should be. At any instant of time, any four coils will be under north pole. The next adjacent four coils will be under south pole. Yeah. If S1 to S4 are under north pole, the polarity induced will be plus minus. That's what we induced, like that's what we are following. Plus minus, plus minus. I'm just marking the polarity. Yeah. Now come next, from fifth coil to eighth coil, it will be south pole. Now it will be minus plus, minus plus. The same thing which we saw earlier slide. It's just now actual connection looks like this one. Minus plus 1, 2, 3, 4. Yeah, from ninth coil it will be again under north pole. North pole convention is plus minus plus minus. And the next four coils, the last four coils will be under south pole. Minus plus minus plus minus plus minus plus. So yeah, now we have marked all the positives and negatives, and this is how our total connection will look like when we connect all the uh, coils in series. And each coil, based on what pole the coil comes under, we also mark the polarities as well. Now polarities is okay, but what about the magnitude of the voltage, like instantaneous value of voltage, how it should be? Because each slot will be under the pole. Now each slot will experience a different kind of magnetic field, that is magnetic field intensity, that is B. Because each slot will have its own. Because the interesting thing is, in a DC machine, if you see, so let's say it is magnetic field intensity, and this is, let's say, space angle. Now this is a pole, right? Let's say this is a north pole or any other north or south pole, and this is how your rotor is. slots slots will be. Now here, uh, okay, here it will be another pole, right? South pole. Now here if you see, under the pole the air gap will be minimum. Under the pole the air gap will be minimum. So between this pole distance, the gap between these poles, the air gap is maximum. So there the magnetic field distribution will be very less, and under the pole it will be very high. So it's like, this is the trapezoidal kind of field distribution you will get. Because why trapezoidal, why not some other shape? Because once it comes under the pole, now your B will get, because air gap is almost constant here, since starting to ending of the pole, so you'll get a constant flux field distribution. Here you can say that this is zero, almost zero, because it's between two different poles, so there is no field there. Once it enters under any pole, you will have magnetic field there. So this is how you will get, right? Now let's say these are the conductors, and this is how angle, as we increase angle we will get a different field distribution. But the actual question is, based on the field distribution only, magnetic field intensity, we will get EMF induced, right? BLV sin theta. As the value of B changes, the value of EMF induced also changes. So that's what the magnitudes will be different when it comes to the amount of instantaneous value of voltage. That is, magnitudes may change because the value of B is changing here. Yeah. So my question is, I want to get a DC voltage out of it. Till now, I have connected all the coils in series, and I have given AC supply, and each coil has been induced with an EMF. EMF is being induced with different instantaneous magnitudes. Now, to get a DC supply from these coils, what I will do is, now here interesting thing happens. Let's see that. I'll take a let me take a different color for that. Let me take a red color. At each junction, what I will do, I will draw. Sorry. Okay. Okay, I will draw a wire. Okay. At each junction, what I will do, I will draw a conducting wire. At the end of conducting wire, I will take a thick copper strip. See, sorry, it's not. How I meant was something like this. At each junction, I am drawing a conducting wire. I will tell you like what's the purpose of this conducting wire and why we are doing this. It will be really interesting because my goal is to get a DC. Till now, I haven't got any DC voltage. Now we will see how we will get a. Yeah. So what I did from each junction, I have drawn out a conducting wire, which is a conducting in nature, and at the end of the thing, I have a thick copper strips. Now, whenever the machine rotates, these conducting wires also rotates along with the coil because they are connected to the coil. So they are not stationary. They will connect along with the machine whenever it rotates. Now what I will do, I will place a brush at such places where I will get continuous positive or negative kind of output. Whenever I take the voltage across those two brushes, I can make sure that that is only DC. Now where to place the brushes, and one more thing, the brushes should be placed, the brushes position should be fixed. That means that let's say these are all the commutator segments, right? Each junction we have drawn that are nothing but the commutator segments. Now I will place, let's say I placed a brush here. Now brush, let me take another color. What happened? Okay. This is the brush number one, and this is brush number two. The placement of brushes should be in such a place that where we get positive, either positive or negative. Now see, the brushes are fixed. Assume that the brushes are fixed, and the machine keeps rotating. Whenever this machine keeps rotating, this particular uh, this particular conducting wire will touch the brush. It will touch the brush and it will move. It will move. Keep on rotating. Whenever it touches the brushes, now there we will get some kind of voltage. So whenever we get same kind of polarity of voltage, then we can actually get that voltage as an output. Now see, the brush has been placed here. So if you see the voltage at this instant, whatever conductor comes at this point, you can see the polarity is always plus plus. Now if you see any other coil, the adjacent terminals are plus and minus. You won't be getting any voltage there. But here, at any instant of time, at any point of time, if you see, the conducting wire will experience the positive voltage only at this point. So this is a B1. Let's say this B1. This is a positive brush. In the same way, where let go through all the terminals and see where you are getting same terminal, same kind of positive or negative. Now if you see, I have placed the brush here. Why? Because you can see here it is consecutively you are having a negative, right? So that I will do as a second brush, B2. It is nothing but a negative brush. Okay. Now again, check, go through all the terminals. You will come across another same terminal. See here again, minus minus is there. At that we'll have, let's say, B3. It's a negative brush, and again see, you will have one more brush like that here at the bottom.
S1.
Yeah, S1, right? So here you have, see, the brush 4 I have placed. Is it a positive brush or negative brush? It's a positive brush. If we have 4 poles, the interesting thing is, since we have 4 poles, we have 4 different brushes, because the orientation is such that whenever we are moving from one pole to another pole, the terminals are interchanging, and at that instant we are getting the same terminal. So that's the interesting part. And we can say that in a latch winding, the total number of brushes will always be equal to total number of poles. That's one interesting thing we have found now. And we will see one more interesting thing. So yeah, Ultimately I want to get a DC output, right? That is plus will be there and minus will be there. Now I have two negative brushes and two positive brushes. I will just connect these two brushes through a connecting wire, that doesn't matter. And now I connected these two. And what I will do, once I connected these two brushes, I will take, yeah, because armature, from armature I will take the supply, right? Now here I will take the supply, this is A1, and here I will take another supply, this is A2. A1 will be positive, A2 will be negative. Doesn't matter, if it is a 2-pole machine we will have two brushes, if we have 6-pole machine we have 6 brushes, but in that 6 brushes 3 will be positive, 3 will be negative. All 3 we will connect and we will take positive there. Next, all negative brushes we will connect and we will take negative there. Output will be 2 only, A1 and A2, that is positive and 1 negative. That doesn't matter. Now, yeah, if you see, let's say my current is flowing from the A1. I started with B1, okay. Now B1, the current will be like that. Current should always move from higher potential to lower potential, right? If my current enters at the positive terminal, it should come back through the negative terminal. Now, can you tell me the path for the current if I start from brush B1? So, I have this path and it should come to negative B2 or B3. How it can reach B2 or B3? One path is, the current will go like this, and this is one path, and this is come like this. This is one parallel path. Okay, parallel path means the path for the current to flow to complete its circuit. Okay, one parallel path we saw. Again, we have another parallel path between B1 and B3, because B3 is negative. It will start, see, it will come like this, go through all these coils, and here it will reach the negative. So this is the second parallel path. So each brush is having two parallel paths for the current. Now the same thing will be repetitive for B4. Now let's say I start from B4 to reach negative. It will start like this. It will come like this, and it will flow through all these coils, and it will come into B2. This is third parallel path. Now again, the last parallel path will be, it will start at B4. It will flow through all these coils, and it will come at B3. This is fourth parallel path. Now what my intention is, whenever a current is flowing through brushes, two brushes are there, positive and negative, the current is getting divided at the armature into four parts, to B1, B2, and after getting into B1, it is again dividing into two parts, B1 to B2 and B1 to B3. That is, another part is, when it comes to B4, it divides into B4 to B3 and B4 to B2. Now how many parallel paths are there in total? Four parallel paths. Now from this I want to conclude, if it is a lap winding, number of brushes will be equal to number of poles. This is one conclusion from the diagram we have. Another conclusion is, number of parallel paths in a lap winding, it's only works for lap winding. For wave winding it's different. Number of parallel paths, let's say we denote it by A, is equals to, again, number of poles. So this is very important relation. Important means, during while you solve any numerical problems, this particular thing is very important. Like, to know how many poles will be there, how many parallel paths will be there inside a. Yeah. Hello. Can you hear me?
Yes, sir.
Sorry, there was a network glitch. Sorry for that. Let me share my screen again. Okay, I think. Okay. Why am I not able to share? Okay. Okay. I hope you can see my screen. Let's just quickly solve a few problems, and we will that. So yeah, you can see here. Uh, you all can see my screen, right? Can someone confirm? We will just solve. Yeah.
Yes, sir.
Yeah, thank you, thank you. So you can see here we were given with a 8-pole machine. 8-pole DC machine has 64 rotor slots. It is housing a double layer simplex lap winding. All coils are full pitched. Full pitch means each coil will have its own full coil span. Coil span will be the same thing we discussed. Each coil will start from one, and it will use the complete coil span. That is full pitched. And slots are numbered from 1 to 64. Okay. How many coils does the armature have? It's very simple. Like if you understood what we have discussed till now, you can just simply by seeing question itself you can just answer it. Let me just draw here saying 1 2 3 4 like that. 64 slots will be there. And how many coils does the armature have? Now before going into coil calculation, now number of slots is equals to 64. That was given in the data. And we already saw for a double layer winding, each slot will house two coil sides. That means total 64 slots will house how many coil sides? Coil sides. Coil sides will be double of the slots, 64 into 2. That means it will house 128 coil sides. Now we know that each coil will have how many coil sides? Coil side 1, coil side 2. Now 128 coil sides means how many coils? 128 by 2, 64 coils. So the answer is how many coils will have? Coils will be also equal to 64. This is how you calculate. But what they say is in a double layer winding, number of slots is always equal to number of coils. That's the relation. In a double layer winding, coils is equals to slots. That's the shortcut. You can remember or you can go through the definition also. It's very easy. Now, yeah, you can see the question 2 here, a subsection of question 2, the same data is same. Now, a particular coil has one of its sides in the slot number 2, okay. Then in which slot the other side of the coil is, if the other side is not in the slot number 2, okay, that's forget about it. Before getting into question, now number of slots is equals to, how many slots? 64, right? 64. And number of poles are, how many poles? 8 poles. From this, what is the coil span? Coil span is nothing but slots per pole, right? 64 by 8. It is 8. It means that we discussed in the diagram. If I start the coil 1 from slot 1, it will end at ninth slot because that's a coil span. And if we start at coil number 2 at this second slot, it will end at 10th slot. Now it's in the diagram. If you see, first slot will end at, slots are there, 9, 10, 10. First slot will end at 9th slot, and second slot will end at bottom slot, 10th slot at the lower one. Now this is first one and this is second one. Now see the question. A particular coil has one of its sides in the slot number 2. Okay, slot number 2 will have two coil sides, let's say. So this particular slot, if you coil side if you take, it will end at 10th slot, that is 2 and 10. But it was given that the other slot, side slot, is not in slot number 10. Now it means that he is not talking about the top coil. He is talking about the bottom coil in slot number 2. Now, where this coil will have its starting end, because the bottom coils all are its ending, the returning ends, right? Where it will start, it is nothing but 64, 63, like that. You have to go back. How you will go back? Because see, somewhere the coil will have 2 dash. We have to find this number. Okay, now it's very simple. Now each coil span is 8, right? If it is 10, you will get the starting coil as 2. How you will get 10 minus 8 is equals to 2? That's how you get back. Now if it is 2, we have to get where it is the back end. We have to minus 8. That is not possible because it's a second one. What we will do, it is 64, right? It is 65, it is 66. Now you subtract 66 minus 8. How much it is? 58. So that means that there is a 58th slot where the top coil is going and returning in the second coil bot. Second coil's returning end. That means 58 2 dash. Because on top of 2 we know this coil is ending at 10th slot. So he was asking about the bottom coil which is starting at the 58th slot. So the answer for this is 58. It's simple. You just have to go back calculation. Coil span, you subtract 8 slots from the second slot. That is 58. Now we have two questions here. How many segments should the commutator have? That's very, it could be confusing if you don't know the meaning of segment, if you don't know the meaning of commutator. I will just go back. You see this diagram, and if you see each coil, if you take each coil will have an extending wire, right? Connecting wire. We talked about connecting wire. Each coil will have one, and each wire will go to a commutator segment, because the ends of this wires is nothing but a commutator segments on which the brush will run. You remember, right? So each coil will have one commutator segment. With that logic, you can see how many segments should the commutator have. The question is how many coils you have, right? Number of coils. The first question we already solved. The coils, number of coils is 64. So coils is equals to number of coils is equals to number of commutator segments. So answer will be same as 64. Okay, how many brushes should the machine have? This should be very simple. How many brushes should it have?
4.
No, it's a 8 pole machine, right? Number of poles is equals to number of brushes. We discussed already. If it's a 4 pole machine, we will have 4 brushes. What we discussed is for a 4 pole machine. Now, since it's a 8 pole, you can see in the question it's an 8 pole machine. For an 8 pole machine, how many brushes? Each pole should have a brush. Okay, now how many parallel paths armature will have? From the theory we discussed, in a lap winding, the number of parallel paths
Sir, 8.
correct, number of poles. you will have the parallel paths as many as your number of poles. It is again eight parallel paths. Now we have to calculate the slot pitch here. So this particular concept is then we discussed in the theory. It will be we will directly discuss here. That's not a problem. Now let's say slot pitch is nothing but, see, this is our slot pitch, right? I will say what is I will talk about what slot pitch is. Let's say it is the entire rotor. Okay. Now it is a 360-degree. The question it was asked is the pitch of each slot. We have 64 slots, right? Each slot will cover how many degrees? Like, what is the pitch of each slot? That was asked theta, but it was asked in theta electrical. Now it's simple. We have 36 slots. 360 by 64. How much is 360 by 64? Okay, it's around, okay, 5.360 by 64. 5.65. Okay. 5.65. So this 360 is nothing but the mechanical angle. So that's the mechanical angle. But what they're asking in the electrical degrees. So that is the theta electrical is equals to P by 2 into theta mechanical. P is nothing but poles. Now how many poles we have? 8 poles into theta mechanical is 5.625. So 5.65 into 4. It's 22.5 degrees theta electrical. You have to make sure, like you have to keep in mind whatever it is asking, is it mechanical or electrical? That's important. Yeah, if it is electrical, it always depends on number of poles, because electrical degrees is not actually equal to mechanical. If only it's a two-pole machine, electrical is equals to mechanical, because 180 degrees will be under one pole, 180 degrees will be under second pole. So it total combines 360 degrees. Mechanical will be equal to electrical. So yeah, I think, yeah, that's it. So yeah, today it was a bit long discussion on the DC machine winding construction, and how to actually decide how many brushes we need, how can we get DC output out of the AC machine. After this session, you please go through once again the today's session, and you will see how interesting it is, how we are getting DC voltage output of DC like from the AC input. Now I hope these concepts are clear for you today, and yeah, you should be very clear on now you should be at this point you should be very clear on what is a slot page, what is a coil span, what is a parallel path, what is like many other factors are there, what is like uh, full page, what is when you talk about slots per pole, what is that mean, what does that mean actually, and these things also should be very clear to you now. Coil, what is a coil, what is a coil side, what is double layer winding, what is single layer winding. These all concepts should be very clear by now, because if you are clear in this only, the concepts which we will be discussing on the further weeks will be very easy for you. So yeah, if you have any doubts in today's discussion, please do ask me. If there are okay, if there are no more doubts, I will end the session here. We will meet in the next week, and please don't forget to join the 7 p.m. session as well. And yeah, thank you once again for joining patiently and listening patiently.